on your notes is just recapping what we've already learned from the last unit. I want you to draw a solution of sodium chloride. And in that picture of sodium chloride, I want you to be sure to label the sodium, chlorine, and then the water molecules, and be sure to orient the water molecules correctly. Okay, so things that you should already know, how they're spaced out, the ratio between the sodium and the chlorine when they're in the solution, and the interactions between the particles. So this is what you should have as you're drawing, and just to recap, remember the sodium ions, they have the positive charge, so the water will orient, the negative oxygens will be attracted to the positive, and then chlorine is a negative 1 charge, so the positive hydrogens are attracted to the chlorine on there. And then we just have some waters in it because it is in solution, okay, and you can have more sodiums and more chlorines, but you need to make sure the ratio is 1:1. Now I want you to just go back to your model and label what you believe the solute and the solvent are in your beaker. Picture the salt, NaCl, those are the solute that was dissociated, and then the water in the solution is our solvent. Now that you understand what the solute and the solvent are, I just want to talk to you about kind of describing how the concentration of something is. So how salty it is versus not salty, okay? So if you have a greater concentration, it means you have more solute in your solution, and if you have like a diluted concentration, that means you have less solute in your solution. This is actually called molarity, and this is how we express the concentration of a solution. Okay, so when we are looking at molarity, the unit that we will use is a capital M. Okay, it stands for molar or molarity, and it's measured in moles per liter. Okay, and you need to make sure that it's in liter and not milliliters. So if there's any conversions that need to happen, you'll do that. The equation for this would be big M equals moles of solute over the liters of the solution. And we're going to do a couple practice problems with this. Okay. First problem that we're going to do, I want you to take a moment and just read through the problem and list out your givens. So just take a moment, list out the givens in the problem, write the equation that you just learned down, and see if you can solve it, and we're going to go over it. You should have these for your givens. We have 7 moles of NaCl. Now that is the solute in the equation, and it's moles. And then our liters of solution was given as 14. So we're looking for molarity here, so we're just going to use the equation as is and plug our values in. So we have M equals 7 moles of NaCl over 14 liters of the solution. Okay, so when you plug that into your calculator, you should get 0.50 because of sig figs, and that would be big M, which is molar. Okay, so that's the unit that we tack on. So this says we have a 0.5 molar NaCl solution. So hopefully you have solved this problem by now. So the first step that you need to do, like I said, is convert the grams to moles of that solute. So this is just using a simple gram to mole conversion. This is taken from the periodic table, the molar mass of FeCl3. Okay, so again, you'd watch the sig figs here, so you get 0.2500 moles of FeCl3 of the solute. And then we had to convert the volume to liters. So to go from milliliters to liters, you divide by 1,000. So you should have 0.500 liters because of sig figs. Then you just plug in, when you get the units that you want, you just plug it into the molarity equation. Okay, so here I'd have 0.2500 moles over 0.500 liters, and that will give me a 0.500 molar solution of FeCl3. Okay?
When you have a solution that you get from some manufacturer, it normally doesn't come to the exact molarity that you want. So you have to dilute that solution. So for example, the hydrochloric acid that we use in lab, or the other acids that we use during that copper cycle lab, we had to take the concentrated solution that we got from the manufacturer and add water to it. So in order to do that, we use this equation. So dilutions use M1V1 equals M2V2. So M1 and V1 are your initial states. So initially the molarity of your solution and the initial volume of your solution, and your volume has to be in liters for both of these. And then your secondary ones are your final states. So molarity after you've done the dilution, or the volume that you desire after you do the dilution. So what this looks like in real life is if we say I have 6 liters of solution of a 2.0 molar HCl is diluted with 3 liters of water, what's the new molarity going to be? So I take that equation, M1V1 equals M2V2, and I plug in everything that I know. So I say I've got 6 liters of a 2 molar solution, so that's my initial volume and initial molarity, and then I want to make 9 liters of solution because I took my 6 liter solution and I added 3 liters of water to it. So I'm making 9 liters, so I want to know what that final molarity is, so I know how it'll react. So I plug this in, chug out an answer, and you should end up with 1.3 molar if you do this calculation. Alright, so when you plug in everything that you get from the problem, we can figure out volume too. So we know that our initial molarity is 3.00 molar and our initial volume is 60 liters. And we know that our final molarity is 1.5 molar. So then we know we want a final volume of 120 liters. But the question asks, what must be added? So how much volume of the water do we have to add to get to that final molarity that we want? So in order to do that, you're going to take that 120 liters that you calculated here and subtract out what you started with. So you started with 60 liters, so you need to add 60 liters of water to dilute it by half. So we're going to take the molarity and see how it applies to stoichiometry now. So if we take this stoich problem, we say if excess zinc is placed in 40 milliliters of 3.7 molar hydrochloric acid, how many moles of gas will be produced? It's an awkward pause. So we've got, first, with any stoich problem, we need to write a balanced chemical reaction. So we've got solid zinc, and I'm mixing it with hydrochloric acid, which is an aqueous solution. And because this is a single displacement reaction, the zinc and the hydrogen will trade places, and we'll get hydrogen gas produced, which is that H2, because it's a Brinkelhoff, and then zinc chloride. And remember, while zinc is a transition metal, it is one of our transition metals with a common charge. So it's ZnCl2, and this will remain an aqueous solution. So we need to balance this equation, put a 2 out in front of the hydrochloric acid, looks good. So now let's go back to our problem. We have 40 milliliters of a 3.7 molar hydrochloric acid. So we're going to take that 40 milliliters and we're going to write it down first. And this is 40 milliliters of HCl. And in order to use this molarity and relate it to this volume, we need to convert our volume to liters. So we'd say 1 liter is 1,000 milliliters. And then we'd say we're now in liters. So this molarity we'll use similar to how we did with density, where it's moles per liter. So we can use that as a conversion factor. Because our liters are on top here, we need to put our liters on the bottom of the conversion factor, making it 3.7 moles of HCl for every 1 liter of HCl. And this is where we can use our stoich. So we're trying to figure out how much of our gas is produced, so how much of our H2. So that mole ratio from HCl to H2 is that for every 2 moles of HCl, we have 1 mole of hydrogen gas that's produced. So we would say 2 moles of HCl on the bottom, since it's on top here so that they cancel, is equal to 1 mole of hydrogen gas. And then, if you did this calculation, you took your 40 and you plugged it into your calculator, divided that by 1,000, and that got you to liters. And then you took that number and you multiplied it by 3.7, and that gets you to moles of HCl, and you can take that and divide it by 2, and that gets you to moles of hydrogen gas, which should be 0.074 moles of H2 will be produced in our final reaction. And we have 2 sig figs here and 3 sig figs here, so our final answer should have 2 sig figs.